Welcome back to the channel. Today we're going to be talking about Pascal's triangle. Now what does this have to do with Pascal's triangle? Well, stick around to the end to find out. Alright, so to draw out Pascal's triangle, we're going to put ones along two diagonals. And in each of these slots, we're going to put the sum of the two numbers above it. So now that we understand how to make Pascal's triangle, let's look at some cool things we can do using it. So another use for Pascal's triangle that you might have seen in school is when you're expanding binomials. So if we take a binomial, like the form a plus b, and we raise that to a power, say we square it, we can expand it out and get an expression that looks like this. Now let's do the same thing, but instead we'll cube it, and it'll look something like this. So let's take these two now and compare them to two rows of Pascal's triangle. And as it turns out, the coefficients of the terms match up with the rows of Pascal's triangle. So this is really useful when you're trying to expand out higher order binomials. Now, let's just read the rows off from left to right. Do these numbers look familiar? That might be because they're the powers of 11, starting with 11 to the power of 0, 11 to the power of 1, 11 to the power of 2, and so on. What if instead we took the sum of the rows? Well, now we're looking at another set that you might find familiar, because these are the powers of 2, starting with 2 to the power of 0, 2 to the power of 1, and so on. When we look in the diagonals of Pascal's triangle, interesting sequences come out. So the first diagonal is obviously just ones. The second diagonal is the counting numbers, or positive integers. And when we get into the third diagonal, this gets a bit more interesting, because these numbers along this diagonal are actually the triangular numbers, or the numbers that are needed to create a triangle. As we go on to the fourth, fifth, and so on rows, we actually can see other numbers or other sequences similar to this. So the fourth diagonal is the tetrahedral numbers, or the numbers needed to make a tetrahedron, similar to the triangular numbers, but in 3 dimensions. And actually this pattern continues for the rest of the diagonals. So another cool thing about Pascal's triangle is that once we start to shade odd numbers, interesting patterns start to emerge. So this pattern you might actually recognize as Sierpinski's triangle, the fractal made of bunch of just different triangles within each other. And this isn't the only pattern that comes from shading in different numbers. When you shade multiples of different numbers like 3 or 5, you can see other patterns that often have to do with triangles. So this is called a Galton board, and it is made by putting nails in this sort of arrangement you see here, which you might recognize as being the 1, 2, 3, so on pattern of Pascal's triangle. So what I'm going to do is I'm going to take this little ball and I'm going to drop it through here, and you can see it just dropped into this slot. So it seems like the path that it takes through these nails is pretty random, and that's because it is. In theory, when the ball strikes each nail, it has a 50-50 chance of going left or going right. I say in theory because in practice I might have nailed these in kind of wonky, or the wind or something else might be kind of affecting those probabilities. But in theory, if this were perfect, it would be a 50-50 probability. So let's just put another one in. So I'm starting at about the same place that this one started, and it's ending up in a completely different spot. Let's try another one. And once again, it's just going completely different. So it's really hard to predict when we just got one ball, but let's try and see when we have many balls. Let's see if we can see like a pattern here. And so now I'm going to put in 50 balls, and well, let's find out. Alright, so here we have all 50 balls in, and well, we're starting to see that these middle slots have a lot more balls in them than the outside slots do. And this makes sense because there is only a few ways to get into these ones. So like in this slot, there's only one way to get to there just by going right every time. And here there's only one way to go left every time. But there's actually many ways to achieve these middle slots. So it makes sense that we have more in the middle and fewer on the ends. And so the theoretical distribution for if we had many balls and they were all in a perfect system is called the normal distribution, which is this sort of bell-shaped curve that peaks up here and is much lower on the ends. And this is used a lot in many different applications of statistics. And in this case, it deviates slightly from the normal distribution because of random variation, but this is a pretty good model to demonstrate it, and it's pretty close to the normal distribution. Alright, thanks for watching. That's all for this video, and I'll hope to see you next time.